So in the world of blockchain, you've always got this fundamental tension, right? How do you get things to be incredibly fast without sacrificing that rock-solid security that makes the whole thing worthwhile? It's the central puzzle. Well, today, we're going to break down one of the most clever solutions out there, a technology that scales Ethereum by making a very optimistic bet. Okay, let's get right into it.
To really get the solution, you first have to understand just how big the problem is. For all its power, the main Ethereum chain can feel, well, painfully slow and expensive, especially when things get busy. We're talking high transaction fees, long wait times. It's a real roadblock. But why? Why is it like that?
The core issue is this massive intentional redundancy. To keep things secure, every single transaction has to be processed and verified by thousands of computers, nodes, all around the world. And while that's what makes it so decentralized and secure, it also creates a huge bottleneck. If your goal is speed, it's pretty much the worst kind of redundancy you could imagine.
So, if the main layer, what we call layer 1, is all clogged up, what do? Well, you build on top of it, and that's the big idea behind layer 2 solutions. The best way to think about it is like adding an express lane that just kind of hovers right above the main highway. And here's where it gets really smart. A layer 2 offloads all that heavy lifting. It can process thousands of transactions super quickly on just a handful of machines. And this is the crucial part, it still uses the main L1 chain to guarantee that all of that work was done correctly. So you get the speed of a small system, but with the security of the massive one. It's really the best of both worlds.
Okay, so we've got this layer 2 concept, but how does it actually guarantee correctness without just redoing all the work on the already congested L1? And that brings us to a specific kind of L2 called an optimistic rollup. The name itself gives you two huge clues about how it works: rollup and optimistic.
A rollup does pretty much exactly what it sounds like. It takes a huge batch of layer 2 transactions, bundles them all together, and posts this compressed summary to the main Ethereum chain. This summary is basically a claim. It's saying, hey, the blockchain was in this state, and when I say state, just think of a complete snapshot of all accounts and balances, and after we processed all these transactions, this is the new correct state. Now for the optimistic part. The whole system just operates on a simple optimistic assumption. Every single claim is valid unless somebody proves it's not. This is what we call the happy path. A manager posts a new state, other verifiers look it over, and if a certain amount of time passes, let's say a week, and nobody objects, then that new state is considered final. It's a system of innocent until proven guilty.
And this slide gives you a great visual for that waiting period. See those green blocks? They're finalized. They've passed the challenge window, they're locked in for good. But then you've got those blue blocks. They're still unconfirmed. They're living in that optimistic waiting period, where anyone can pop up and say, hold on a second, I think I see a problem here.
But that whole optimistic assumption? It's a huge bet. And it leads to the most important question of all, right? What's to stop some bad actor from just posting a totally fraudulent rollup, stealing a bunch of money, and breaking the whole system? Well, this is where the security model gets really clever. It's all a game.
So yeah, let's play this out. Imagine some manager posts a rollup that has a fraudulent transaction inside. Maybe they tried to pay themselves $1 million out of thin air. What happens next?
The answer is all about economic incentives. See, just to be able to propose a new block, managers have to lock up a significant amount of their own money. That's their stake. If someone challenges what they've posted, the layer 2 chain just pauses, and this dispute protocol kicks off. It's literally a game, refereed by a smart contract on the L1 chain. And the loser doesn't just lose the argument, they lose their entire stake. The whole thing is designed to make cheating a really, really bad financial move.
So let's meet our players. We've got Alice, who proposed the rollup. She's claiming that after, say, 1 million computational steps, the chain correctly moved from state A to state B. And then we've got Bob, an honest verifier who sees the fraud, he stakes his own money and yells, "I challenge that!"
Now, the L1 chain does not want to re-execute all million steps to find the fraud. I mean, that would defeat the whole purpose of the layer 2. So the referee contract forces Alice to cut her claim in half. She has to say, okay, the halfway point of the computation is state C. Getting from A to C took 500,000 steps, and getting from C to B took the other 500,000.
So Bob looks at this, and he knows the fraud happens somewhere in that first half. So he narrows his challenge. I agree the second half is fine, but I'm challenging the first half. Now Alice is forced to do it again, breaking down those first 500,000 steps into two new chunks of 250,000.
And this image here gives you a perfect idea of what's happening. They go back and forth, cutting the assertion in half over and over again. This bisection game, as they call it, very efficiently zooms in from 1,000,000 steps down to a few thousand, then a few hundred, and finally, it pinpoints the single specific computational step where Alice and Bob disagree.
So, and here's the absolute key. Once the disagreement is narrowed down to just one single instruction, that is the only thing that gets executed on the main L1 chain. The L1 acts as the ultimate impartial judge. It runs that one tiny step, and it immediately sees who is telling the truth. Alice is exposed as a fraud, she loses her stake, and Bob gets rewarded for being honest. And just like that, security is maintained without killing scalability. It's brilliant.
Now, this might all sound like some complicated theory, but this stuff is already out there, processing billions of dollars in transactions. So let's take a look at how it all fits together in a real-world system.
This diagram here shows the architecture of Arbitrum, which is currently the most popular L2 on Ethereum. Let's just follow the flow for a sec. You can see transactions coming in on the left, but notice this new role right in the middle, the sequencer. This part is key to making the whole thing feel super fast for the user.
So the sequencer's job is basically to grab all the user transactions as they come in, put them in a definitive order, and give you an instant confirmation. Now, this is a soft confirmation. It's not fully secured by L1 yet, but for you, the user, it makes the experience feel instantaneous. The sequencer then bundles, compresses, and posts all this data to the L1 chain, where it gets final ironclad security after that challenge period is over.
So what's the big takeaway here? Why does this all matter? Well, optimistic rollups are dramatically faster and cheaper because they move all that heavy computation off the congested main chain. And yet, they are incredibly secure, anchored to Ethereum, and protected by a game that only needs one single honest person watching to keep the entire network safe. That's amazing, and this opens the door for much more powerful and complex applications. The main trade-off, of course, is that week-long wait for withdrawals, but for most of what you do day-to-day, the speed is an absolute game-changer.
So this technology pretty much solves the scalability problem, right? We get speed and low cost while inheriting the bulletproof security of Ethereum. It really makes you wonder, with this huge piece of the puzzle falling into place, what's next? What becomes the next great frontier? What kind of new challenges and amazing opportunities open up now that blockchains can finally operate at the scale of the internet itself?